Great. Okay, we're going to move on to Joel Maia from FCT. Welcome, Joel. It's good to have you back. Joel graduated in mechanical engineering with a focus on thermofluid dynamics in 2002 in Brazil. An MBA followed in 2015 in a joint educational program between Austria and the USA. Since 2001, he's held a number of roles working on projects across more than 70 countries, but always related to combustion and energy-intensive industries such as cement, lime, steel, and other minerals. He joined FCT in 2016, where he is now CEO based at the company's European headquarters in Vienna, Austria. And he's going to talk to us about decarbonizing cement production, the role of alternative fuels. Over to you, Joel.
Hello, hi. Can you hear me properly?
Yes, we can hear you.
Very good. So thank you for the introduction. Today, the target is to talk a little bit about the alternative fuels in the decarbonizing the cement production. I would like to start, first of all, giving an overview. So we start here. Once upon a time, there was a planet called Earth. There were some people living on it, and then these people became more and more. And today, we are around 8 billion people, right? It's expected that by 2050, we will be 2 billion more. And this 2 billion more, this means roughly one New York size amount of people per month new in the planet. And all these people will need infrastructure, housing, energy, and so on. And this infrastructure is still, 60% of it still needs to be built by the year to 2050. So there's, although there's a lot already made today, there's still, the majority still has to be done. Obviously, this growing in population also brings some challenges for the planet. So this means more infrastructure, this means more energy demands, this means more construction materials. And at the end, more natural resources are used for it. So what does this mean for us? So this all has an immense impact on the environment, especially global warming is a problem that we all are facing these days. Sorry, this jumped to the wrong slide. One moment, please. So there is a, can you see again? Yeah. So there is an immense impact on environment, global warming, and then I don't know why this is not really jumping to the proper page. I try again. All right. And the question is, okay, are we doomed? Is this the end of the times? The answer is no. But this answer no comes with a big if we all do what has to be done. When we say all, it means as individuals. So if we look into the waste hierarchy pyramid, I think there's a lot we can do to avoid the environmental problems that we are facing these days. So everything we can do on the top of this pyramid is better than what we have to do at the bottom of it. So if we can reduce the use of some resources is better. If we cannot reduce the use, we should try to reuse the materials. If we cannot reduce or reuse the materials, we should try to recycle them. And all this we can do as individuals very easily. We should obviously avoid the last step, that is disposal, because this is what is being in the environment for many, many years. And it's a combined effort from everybody. And especially in terms of industry, that's where we all are working today. We are focusing on the repair and recover of materials to be reused as energy sources, for example. When you are talking about CO2 emissions, it's well known that cement production is responsible from 6 to 8% of the man-made CO2 emissions. Here is a chart how this has evolved since the Second World War until some years ago. So it has drastically increased. And when we look from the million tons of CO2 produced by the cement industry, we can see That part of it is caused by process emissions. So basically, the majority of it is by process emissions, basically from the CO2 from the material. And here we can talk, for example, how to reduce it. We can talk about calcined clay. FCT is also working on the calcined clay business, but it's not in the topic of this seminar, of this conference. So this webinar. If you want more details about calcined clay, you can visit our website or send me an email, and we can schedule a meeting. And there's another part, the blue part, is caused by fewer electricity emissions. And here, for example, one way to reduce it would be the use of alternative fuels. We all know this diagram, the clinker mineralogy with the phases of the clinker. Basically, there are two main sections here that should be highlighted. One first phase, from the drying of the raw material until the transition zone of the kiln is let's say a preparation phase where the raw material is being prepared for the clinkerization, and then a second phase that has a very strong influence in the clinker quality and later on the cement quality that incorporates the clinker in the cooling. We need to make this division into these two parts because depending on which the alternative fuels will be used in a different way. When we are talking about the first part, about the preparation part, the calciner, to choose an injection point of alternative fuels in the calciner is like choosing a house, right? When you want to buy a house, you always are worried, how is the neighborhood, how is the environment around it, how is the transportation meanings around this area, and so on. And for the calciner, for injecting alternative fuels in the calciner is the same. So how is the temperature distribution in the calciner? How is the oxygen content in the different areas? What's the velocity profile? What's the residence time? So basically, you are more worried about the flow characteristics inside the calciner. And for this, I think it's, for example, to find the better position to inject your alternative fuels and be able to maximize it. One way to do this would be through a CFD study. We can also do some, this is a result from some CFD that we made in the past. Or this would be more for alternative fuels that have good aerodynamic characteristics, mean that they fly together with the gases. In other cases, when we are talking about complete tires and so on, we can talk about a pyrorotor, for example, or some other type of combustion equipment that can deal with these larger particle sizes. But for smaller particle sizes that can fly very well, a CFD study is a good way to check if an existing calciner can deal with the intended alternative fuels, or if a modification is necessary, an enlargement of the calciner is required, or modifications on the top of the calciner for a better mixing, and so on and so on. So this all can be done through CFD. This is also not covered by this presentation today. Today we will focus on the kiln. So. And then there's a difference when we are talking about the kiln. We can make an analogy to a sports car. To my Italian friends watching now, you all know this car. Choosing how to fire the alternative fuels in the kiln is more about performance. So if you would buy such a car, you would be worried about which power it has, what's the maximum speed, how efficient aerodynamically it is, how it can turn, and so on. And it's the same about the burner, right? So if you're injecting alternative fuels in the kiln, you are worried about how much you can use, what are the mixing efficiency of this burner, how you can control the particle, the alternative fuel particle direction, and so on. To inject alternative fuels at the kiln side, that's the main topic of this presentation today, there are two main options. One would be to use a satellite burner in the kiln hood. So if you can see here, let me put here a laser pointer. So if you can see here, so the alternative fuel, the satellite pipe would be positioned a little bit above the burner, so in the secondary air. And this is a good solution up to a certain point, because the secondary air has the majority of the air required for the combustion, right? Above 95% of the air in the kiln is coming through the secondary air. This is a zone with high temperatures, so we are talking about 900,000 degrees. However, this region has a very low control in mixing. You have a very low control over the mixing and then injection conditions on the secondary air. A second option would be to use a modern high substitution rate alternative fuel burner, like the one in the picture. And in this case, you would inject the alternative fuels through the burner itself. Again, there are some benefits on this solution, and the main characteristics is that through the burner, you're injecting just a small amount of the air required for the combustion. We are talking about 8–12%, depending on the type of kiln, a bit more, a bit less. At this zone, you have, especially closer to the burner, you have lower temperatures. However, the main advantage is that you have a very high control and a very intense mixing of the alternative fuel with the remaining air around. If we talk a little bit about satellite burner first, so option number one, injecting the alternative fuels on the top of the burner directly in the secondary air. This is a rendering of a typical satellite burner. So first of all, this satellite burner would have an adjustable position in terms of angle, penetration, and so on. And the main reason is to influence the flight path of the particles. So you could adjust the position of this satellite burner depending if you are using a higher, heavier particle size or a lighter particle of alternative fuel. Also, this pipe has refractory for increasing the lifetime, and at the front of the satellite burner, you have an additional injection of air through these holes, and this is to give you an additional control over the flight path of the particles as well as the combustion. Main advantages of such type of satellite burner is that as you are injecting the alternative fuels before it comes to the main flame, so there is a time between the injection point and the start of the combustion of this alternative fuel, so you have a pre-drying while this alternative fuel is flying. You also have a preheating because the alternative fuel is being injected into a 900,000 degrees environment. It's very easy to install, so you don't need the investment. CapEx is very low for that. And it's the ideal solution to start with alternative fuel at the kiln side. Very cheap, very easy to install, fast. And you can have a very fast return on investment, and also you can decrease the CO2 emissions almost immediately. However, there's a drawback. Obviously, this is not the main burner. So when you look inside the kiln, the majority of the fuel should be in the center of the kiln, and now you are injecting alternative fuel on the top of it. So you have a limitation about the substitution rate that you can have through this pipe itself. We have seen cases maximum at around 60%, but mostly these are in the range of 40, 30, 40, 45%. As I mentioned, the majority of the fuel should still be, let's say, at the main flame coming from the main burner. So when you start shifting too much energy to the satellite burner, you are injecting more fuel through a burner that is not as capable as the main burner itself. So it starts making not much sense. Option number two would be to inject, as I mentioned, the alternative fuel through the burner, and then you need a kind of burner that is optimally designed for the combustion of alternative fuels. Years ago, we started looking what this optimum design means, and we came to a question. So what if we take a standard design of a burner, as we can see here? So we have some axial air, you have coal, pet coke, lignite, and then a through air channel. What if you change the arrangement of the axial air? So again, the same picture. So something is going on here with the presentation. Let me go back to the correct slide. I'm not sure why this is happening. One moment. Sorry for that. So let's try again. Yeah, and then our question was, what happens if we change the arrangement of the axial air? So first of all, we try to study the difference between if we have the same amount of axial air, same injection area, same speed, same pressure, if we just change the number of holes from, let's say, 36, we go down to the half, to 18 holes. A bit bigger holes because it's the same area, but the same, but different number of holes. And then the next question was, okay, what happens if we take these holes that we have now and we group them 3 by 3, leaving a large area empty in between? So we, as I mentioned, we have in our company a CFD department. We try to study this, first of all, in the CFD. So from the CFD, we can get, for example, among many other parameters, results, we can get the radiation from the flame to the clinker. It would be a chart like this. So here at 0 would be the burner, at 17 is the kiln inlet, and we can see here on the vertical axis, the radiation from the flame to the clinker. From this chart, there are two main parameters that we can read. One would be the peak value of the radiation, and the second would be the area below the curve near in the clinkerization zone. So this is how much energy is transferred to the clinker in the clinkerization zone. If we look to this chart, this is the typical burner. We compare it to the burner with larger holes in a smaller quantity. We can see that the peak radiation increases, and the flame later, after the clinkerization zone, gets colder, so the flame is a little bit shorter. And when we compare this to the next option, that would be grouping the orifice 3 by 3, we can see a further increase in the radiation and a further reducing of the flame length. So what this means is that in the green configuration, so the grouped 3 by 3 holes, we can achieve a much more intense and short flame. From one side, this is good because if you are trying to increase the amount of alternative fuels are a little bit harder to burn. So you want to have an intense flame to allow a higher substitution rate of this by these alternative fuels. But from the other side, in case you have a problem with your alternative fuel dosing system or from the supply of the alternative fuel and you are burning coal this day, you don't want to have such an intense flame because this would generate a lot of NOx, right? So what was the solution that we found? So we can have the same burner operating two extreme modes. So one mode would be what we call standard mode, in which we have air being supplied through all axial air orifices. This generates you a milder flame, not so intense, suitable for operation with traditional fuels, for example. And then closing a valve outside the burner, you don't stop, you reduce to a minimum, because you can see here that you still supply a little bit of air for cooling and avoid clogging. But from process purposes, this amount of air is very small. And then you're supplying the majority of the air to these 3 by 3 orifices. With this, you create a higher speed here, and also you create a gap through where secondary air is sucked inside the flame. And here you would have this much higher, much intense flame, much shorter flame, suitable for the use of alternative fuels. Just to illustrate here a little bit more, so these are the lines of the secondary air only. You cannot see here fuel or anything else. If we take a section a little bit in front of the burner, we can see here that in the standard mode, there is a certain quantity of air coming inside inside the flame. And when we engage the boost mode for alternative fuels, we can see that there's much more secondary air coming to the flame. And this is especially important because, as I mentioned before, the majority of the oxygen required for the combustion is coming from the secondary air. So as the faster you can draw secondary air into the flame, the faster will be the combustion of your alternative fuels. All right, and then there are obviously other additional features like some lofting air, as we call it, for alternative fuels. So you can see these small holes injecting air at the end of the alternative fuel pipe. You can see here in the picture. We divide them in two groups, so you can see the pink lines on the top and the green lines on the bottom. They can be controlled separately, mainly because alternative fuels change from time to time. If you're talking about a heavy, more 3D alternative fuels, we would use this green injection of air here, mainly to lift the fuel itself. And if we are talking about a lighter fuel, like a good RDF, we would use both the pink and the green, basically to disperse the fuel in all directions. Additional to this, we have some wear protection pipes. So inside the alternative fuel, we can use some pipes from Castellane, for example. And here you have a wear line face. So the wear in these pipes is much, much reduced, and therefore we can increase the lifetime of the burner. This is one of these burners, TurboFlex, as we call it. So you can see the different size and position of the axial air holes. You can also see the lofting air inside. And with this, we can achieve up to 90% SRF RDF through the kiln burner itself. I have a video here. I hope you can see it. There's no audio, but the idea here is to show how it would look like when we are talking about 80% SRF, 20% pet coke at the kiln burner. So we can see here there's a very short ignition zone of the fuel. The primary cooling zone inside the kiln is also very, very short because we are having a very fast ignition of the fuel, very intense and short flame. We don't see much alternative fuel landing on the bed, which is also a good thing mainly for the clinker quality. And you can see from this video the difference between a good burner burning 80% SRF and not with a good oil or something. We are talking about 20% pet coke as the balance, against another burner that would be lacking performance, a lot of material falling onto the clinker, creating reducing zone, brown clinker, etc., etc., etc. So this was more or less the topic for today. I just go through the company quickly in the next 2 minutes, 1 minute. FCT, we are a group of 3 companies. One is FCT Combustion, that we are dealing with everything related to combustion for heavy industries, for example, alternative fuels, kiln burners, calcined clay, hydrogen, and so on. FCT Tech, that they are making online process control equipment, and FCT Flames, that we are making entertainment flames for Olympic Games, for example. Our company is from 1984. We are experienced in several industries, mainly cement, lime, and minerals, worldwide presence. We can see our 5 main offices here on the screen, and we have more than 1,000 combustion systems as references. And we are serving different industries: cement, iron ore, lime, pulp and paper, mining, lithium, bauxite, etc. And the main advantage of this is that we can make a crossover of technologies between one industry to the other. Speaking about the cement plant, we have a group, or group of engineers now is able to help in different parts of the plant. So fuel handling, pyroprocess line itself, calcined clay, and gas treatment systems. Here are some of our key products. I'm not go into details here for the lack of time, but different technologies for rotary kiln burners, hot gas generators, different types, calcining systems, including rotary kiln and flash calciners for calcined clay, fuel handling systems, burner management systems, different types of services like audits, CFD, and so on. Including when we're talking about clay, we have 2 test facilities in Brazil. One would be a rotary kiln for up to 1 ton per hour. Another one would be a flash calciner up to 50 kilograms per hour. And here just some pictures of recent supplies that we had. For example, flash calcination system, control panel, burners and valve trains on the top for iron ore pelletizing industry, rotary kiln burners for high substitution for alternative fuels, hot gas generator for alternative fuels as well, and hot gas generator for natural gas in this case. Some of our clients, different clients in different industries, different parts of the world. And I wanted to end this presentation with this slide. So at the end of the day, the planet will still be here. The question is if we as humans will still be here as well. So thank you very much. And here are some of our contacts. And in case of questions, I'm happy to answer them.
Thank you very much, Joel, and some deep thoughts at the end regarding our longevity on Earth. A very good presentation. You really, it's to get the burner in as well is completed the whole picture for this webinar. I've a few questions in terms of the fuel mix. What is the optimum for a burner that of your type? Is it the SRF 80% and then petcoke 20%? Is that a kind of typical thing that you're seeing?
I think it depends very much on the region. So if we're talking about Europe, every burner now that we sell in Europe is designed for 80–90% alternative fuels. And then alternative fuels is what the client has around the plant. So most of the times is an RDF type. But also there are some countries with a lot of biomass. So we are talking about meat and bone meal sometimes. We are talking about biomass from local agriculture products, so some rice husk or whatever. But in other parts of the world that the alternative fuels are not so common yet. So we are talking about, I don't know, petcoke or traditional fuels. So there are parts of the world that we sell burners for 100% natural gas, for example.
Mm-hmm. Yeah. Well, what's the highest percentage replacement that you've seen with biomass?
No, we are seeing about 90% as a maximum. 90%. Obviously, it could go depend. So the burner itself is just a part of the equation, right? I think the other part is also the fuel that you are using. So if the fuel has, as discussed before by my colleagues, if the fuel has 20% moisture, I think we would need to go through some combustion theory that we don't have time today. But before you start burning the fuel, you need to dry the fuel. So if you have 20% moisture, it would take you a certain time to dry this fuel in suspension in the kiln and then start to burn it. So this means that the flame would get very longer and the amount of fuel that you would be able to use in this condition would be lower. So, but if you're talking about a good RDF, well prepared, not so big particle size, not so big moisture, then we are going up to 90%.
Have you seen much use of hydrogen, and how does that affect your burner configuration? And what kind of rates can you? I mean, it's a bit of a catalyzer. So does it help offset some moisture, or how does the balance work?
Correct. I think hydrogen is a very, let's say, very hot topic at the moment for the last year and a half. We are involved on these discussions as well. To burn the hydrogen is very easy. So hydrogen is a fuel that burns very, very easily. It's similar to injecting oxygen, so it improves overall the flame conditions. It helps to burn some fuels that are not so easy to burn. So, for example, with a higher moisture. The problem with the hydrogen is that there is not enough hydrogen available, and the cost. So we are not still today. We are not in the days to discuss how the burners are able to burn the hydrogen. It's more a question of if you can get hydrogen to your plant. So what we have seen is up to now at least. Very small amounts of hydrogen being used. And when we say small, we are talking about a few percent, so 1 to 3%, not more, simply because of availability. There were tests being made with higher quantities, but short tests like 1–2 hours maximum.
Yeah. Okay. Very, very interesting. There's a question, which burner would you select out of preference, the satellite burner or the main kiln burner?
I think it depends where the plant is regarding the alternative fuel. So if your plant has no alternative fuel in the kiln burner, I would start with the satellite burner. Because it's cheap, it's simple, you can go up to 40–50% substitution rate, and then you can start from there. So it's a very cheap and easy start. Afterwards, when you are already at this 50% of the kiln, you want to go further, then you should invest on a proper designed kiln burner for that.
Oh, very good. Okay. Well, thank you very much, Joel. That's really an excellent presentation to round off today's webinar. I'd like to thank all speakers, Eugene, Jens, and Joel for taking part today. Really a fantastic selection, and you can see the strength of the feedback and the questions, which has been fantastic. So thanks to everyone who's tuned in today. We'll be back next month, but for now, that's pretty much everything. Please keep in touch. Don't forget to visit Cemnet and check out our subscriptions. Also, more information on our next in-person event, which will be taking place in Jakarta in June. That's coming up in the future. But for now, many thanks. Thanks to our speakers and to all of you for listening. Goodbye.
Thank you very much. Thank you.
Okay.
Bye.
Bye-bye. Thank you.